Extension of the multiplication rule to 3 or more events. If you look at the first point on the slide, you'll recall that in our previous lessons, we focused specifically on the multiplication rule for just 2 events. We used this rule to determine the probability of 2 events, let's call them E and F, happening at the same time. However, life isn't always as simple as just 2 outcomes. In many real-world scenarios, we encounter situations involving 3, 4, or even more events occurring one after another, or all at once. Because of this, today's lesson is all about expansion. We are going to learn how to generalize that multiplication rule we already know, so that you can confidently calculate probabilities for these much more complex, multi-event scenarios. Let's move on to the next slide to see the core concept behind this expansion. Welcome, everyone. Today, we are going to build upon what you have already learned to tackle more complex probability problems. Understanding the concept. The fundamental idea behind the multiplication rule is the realization that in a sequence of events, the probability of what happens next actually depends on the outcomes that came before it. It's all about that chain reaction. So, how do we actually handle this when we move from 2 events to 3? Let's say we have events E, F, and G. The trick is to apply the 2-event rule we've already learned, but we do it iteratively, which is just a fancy way of saying we apply it step by step, over and over again. To make this concrete, if we want to find the probability that events E, F, and G all occur together, we break it down into a logical sequence. First, we look at the probability of event E occurring. Next, we look at the probability of event F occurring, but specifically under the condition that event E has already happened. And finally, we look at the probability of event G occurring, given the fact that both event E and event F have already taken place. Now that we've established that we are moving beyond just 2 events, let's really dive into the core concept here. In the next slide, we are going to see the formal mathematical derivation of how these steps are linked together into a single formula. Mathematical derivation. Now that we understand the concept of applying the rule iteratively, let's move on to slide 3, where we will mathematically derive the formula for 3 events, E, F, and G, within a sample space. This derivation is crucial because it provides the logical foundation for the generalization we will see in the next slide. First, let's look at step 1, which is grouping the events. To make this complex problem manageable, we are going to treat the intersection of the first 2 events, E intersection F, as if it were just one single combined event. Because of this, the probability of all 3 events occurring, which we write as the probability of E intersection F intersection G, can be rewritten as the probability of the intersection of the event E intersection F and the event G. Moving to step 2, we apply the multiplication rule for 2 events that you already learned in the previous lesson. Remember the rule where the probability of intersection B equals the probability of A multiplied by the probability of B given A in our case. We let event A be the combined event, E intersection F, and event B be event G. When we apply this, the probability of E intersection F intersection G becomes the probability of E intersection F, multiplied by the probability of G, given that E and F have already occurred. In step 3, we need to expand that first term. We already know from our previous studies that the probability of E intersection F is simply the probability of E, multiplied by the probability of F given E. Finally, in step 4, we perform the final substitution. We take the expression we just found in step 3 and plug it back into our equation from step 2. This gives us our complete formula. The probability of E intersection F intersection G equals the probability of E times the probability of F given E times the probability of G given E intersection F. Just as a side note, you might see this written more compactly in your textbooks. Since the intersection of E and F can be written simply as EF, the formula is also expressed as the probability of E times the probability of F given E times the probability of G given EF. This is the exact same logic, just written more efficiently. Generalization to N$ events. Now you might be wondering, does this only work for 3 events? Well, the beauty of mathematics lies in its patterns. As we just saw in the derivation on the previous slide, the logic we use to expand the rule for 3 events doesn't actually stop there. This logic extends far beyond just 3 events. In fact, this principle can be applied to any number of events, which we can represent as e sub 1, e sub 2, e sub 3, all the way up to e sub n. So, if we want to find the probability of the simultaneous occurrence of n events, that is, the probability of the intersection of e sub 1, e sub 2, e sub 3, through e sub n, the formula follows that same chain-like pattern. It is equal to the probability of e sub 1, multiplied by the probability of e sub 2 given e sub 1, multiplied by the probability of e sub 3 given the intersection of e sub 1 and e sub 2, and so on, continuing through the entire sequence until we reach the final term, the probability of e sub n given the intersection of all preceding events from e sub 1 through e sub n minus 1. It looks complex, but it is simply the same repetitive process of updating our conditions. To see this theory in action with actual numbers, let's move on to our next slide, where we will walk through an illustrative example involving colored balls in a bag. Illustrative example. Now that we have derived the general formula, let's apply it to a concrete scenario to see how it works in practice. Imagine we have a bag containing 5 red balls, 4 blue balls, and 3 green balls. We are going to draw 3 balls from this bag, one after another, and importantly, we are doing this without replacement. Our objective is to calculate the probability that the first ball drawn is red, the second is blue, and the third is green. To solve this, we will follow a systematic, step-by-step approach. In step 1, we must clearly define our events. Let E represent the event that the first ball is red. Let F represent the event that the second ball is blue. And let G represent the event that the third ball is blue. We are looking to find the probability of the intersection of all 3 events, which we write as the probability of E intersection F intersection G. Moving to step 2, let's calculate the probability of our first event, P of E first. We find the total number of balls in the bag by adding 5, 4, and 3, which gives us 12. Since there are 5 red balls, the probability of event E is 5 over 12. In step 3, we calculate the conditional probability of F given E as I mentioned earlier. This is a without replacement scenario. Because the first red ball was not put back, the total number of balls in the bag has decreased to 11. However, the number of blue balls is still 4. Therefore, the probability of F given E is 4 over 11. In step 4, we find the conditional probability of G given the intersection of E and F at this stage. We have already removed 2 balls, 1 red and 1 blue. This means our new total is 10 balls. The number of green balls remains at 3. So, the probability of G given E intersection F is 3 over 10. Finally, in step 5, we apply the extended multiplication rule that we studied in the previous slides. We multiply the probability of the first event by the subsequent conditional probabilities. This means we take the probability of E, multiplied by the probability of F given E, multiplied by the probability of G given E intersection F mathematically. This is 5 over 12, multiplied by 4 over 11, multiplied by 3 over 10. When we multiply the numerators, we get 60, and when we multiply the denominators, we get 1,320. Simplifying the fraction 60 over 1,320, we arrive at our final result, 1 over 22. As we move to the next slide, pay close attention, as I will highlight some common pitfalls to avoid when performing these types of calculations. Common mistakes. First, watch out for forgetting to update your sample space. This is perhaps the most frequent mistake I see. If you look back at the ball drawing example we just worked through, we started with 12 balls. A common error is to use 12 as the denominator for all 3 probabilities. However, remember that in without replacement scenarios, every time we take a ball out, the total number of balls left in the bag changes. Your denominator must decrease by 1 for each subsequent event to reflect the new reality of the sample space. Second, be careful not to ignore the condition. It is tempting to simply calculate the probability of the third event, g, as if it were a standalone probability. But as we saw in our derivation, we cannot do that. We must calculate the probability of g, given that both E and F have already occurred. Always remind yourself that the third event is dependent on the outcomes of the first two. Finally, do not confuse this method with the rule for independent events. If the events were independent, you could simply multiply the individual probabilities, where the probability of E, F, and G equals the probability of E times the probability of F times the probability of G. However, the extended multiplication rule we have learned today is specifically designed for dependent events, where one outcome directly affects the next. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the formula, it is very easy to make small errors that lead to the wrong final answer. Keep these 3 points in mind, and you will avoid the most common traps in probability problems. Key takeaways. First, remember the fundamental principle we've been working toward. The probability of multiple events occurring in a sequence is found by taking the product of the probability of the very first event and then multiplying it by the conditional probabilities of every subsequent event. It's all about that chain of events. To put this into a concrete mathematical form, let's look at the formula for 3 events. The probability of the intersection of event E, event F, and event G, which we can read as the probability of E and F and G, is equal to the probability of E multiplied by the probability of F given E, multiplied by the probability of G given E and F. As we saw in our ball and bag example earlier, the most important thing to remember is that this rule is applied sequentially. This means that at each step, you must account for the updated state of your sample space. If you are drawing without replacement, your denominators must change to reflect the new reality of the bag. Finally, don't forget that this logic isn't limited to just 3 events. As we discussed in our derivation slide, this principle can be extended to any number of events, which we call n. You simply continue this chain of conditional probabilities for as many events as you have in your sequence. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. I hope this clarification helps you master the extended multiplication rule. Keep practicing, and I will see you in the next lesson.